if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole.
The Big Bang Theory suggests that since the universe came into existence, it is expanding. Space is flat, which means it expands in every direction without curving negatively or positively. However, a fundamental question arises: what is it expanding into? What lies beyond the bounds of our universe? Now, what if I told you that we are living inside a black hole? Our whole universe lies inside an enormous black hole, and it is expanding into that black hole. This may seem an outlandish concept, but there is evidence that supports it. What's more interesting is that famous physicist and Professor Brian Cox has recently made a bold announcement suggesting that our universe could indeed be expanding within an immense black hole. But what is the evidence to prove it? Let's dive in and explore this fascinating idea that will leave you scratching your head. Modern astronomers and theoretical physicists agree that our universe began with a colossal event known as the Big Bang. However, certain perplexing phenomena, such as dark matter, dark energy, and cosmic expansion, have compelled some astronomers to reconsider our understanding of the early universe. You see, our universe seems to be constantly expanding and cooling down. It all started approximately 13.8 billion years ago, when the universe was born in a blazing hot explosion called the Big Bang. Yet there is a captivating and seldom discussed possibility within the realm of modern physics. What if our universe is actually nestled within the confines of a black hole? Several scientists are now entertaining this extraordinary idea, striving to establish a connection between the singularity found within a black hole and the singularity present during the Big Bang. While it may seem peculiar and mind-boggling, the notion is rooted in solid mathematical principles. Surprisingly, it may provide the most plausible explanation for how our universe came into existence and the bewildering phenomena we observe today. Let's dive into this fascinating concept. At the time of the Big Bang, the universe existed in a state of remarkably low entropy, meaning it was highly ordered. Since then, entropy has been steadily increasing over the past 13.8 billion years. Now, you may wonder, what is entropy and why is it significant? Entropy is a measure of disorder and randomness within a system. In general, the universe tends to evolve towards disorder. It's like the way a tidy room becomes progressively messy over time if left unattended. However, the Big Bang defied this natural tendency. It was an exceptional and highly ordered event. This leads us to ponder why the universe embarked on such an ordered trajectory. This question is considered one of the most significant puzzles in the field of physics. To address this enigma, some physicists propose that the Big Bang was akin to a quantum fluctuation, an unforeseen fluctuation that occurred and gave birth to the universe in an exquisitely ordered state. This would mean that the universe, as we know it, burst into existence from a state of extreme order. Since that momentous event, the universe has been gradually moving towards a more disordered state. The degree of disorder, in turn, affects the likelihood of spontaneous creation. Allow me to explain further. When something possesses a high level of order, the chances of it spontaneously coming into existence are rather slim. On the other hand, as things become less ordered, the probability of spontaneous creation increases. Think of it this way. If your room is meticulously arranged with every item in its proper place, it is highly improbable that a new object will suddenly materialize out of thin air. However, if your room is cluttered and disorganized, the chances of something appearing out of nowhere become progressively higher. This is why, over time, things tend to become more disordered. So, applying this principle to the universe, we can deduce that the universe we observe today, which is less ordered than during the time of the Big Bang, is more likely to have come into existence through a fluctuation occurring in the present rather than during its initial inception. In fact, considering the vast expanse of the entire universe, including ourselves and everything within our observable realm, it becomes overwhelmingly more probable that our existence is the result of a fluctuation rather than the original Big Bang itself. This disparity in likelihood is staggering, reaching billions and trillions of times the higher probability. Now, let's shift our focus to black holes. Extraordinary cosmic entities that continue to challenge our understanding. Black holes are objects of immense gravitational pull, so strong that nothing, not even light, can escape their grasp. Some black holes observed today are billions of times more massive than our Sun. These enigmatic entities play a pivotal role in our universe, being essential components of every galaxy, including our own. They are believed to arise from the remnants of a massive star that has exhausted their nuclear fuel and undergone a catastrophic gravitational collapse. The resulting black hole possesses an incredibly compact mass crammed into a minuscule region of space called a singularity. The singularity is a point of infinite density where the laws of physics, as we understand them, break down. It represents a realm where our current knowledge falls short. While black holes remain enigmatic, they are not entirely devoid of scientific understanding. They influence the dynamics of galaxies, shaping their structure and behavior. Black holes can engulf nearby matter, causing it to spiral inward and form an accretion disk, a swirling disk of hot gas and dust. The material in the accretion disk emits intense radiation, making black holes detectable by telescopes and revealing their presence even in the vastness of space. In recent years, scientists have made significant discoveries that have expanded our knowledge of black holes. This research began in the 1970s with Stephen Hawking, who proposed groundbreaking ideas about space and time. While we may think of space as a place where we live and time as a continuous flow, the study of black holes has shown that they reveal fundamental elements of space and time. Black holes serve as a metaphor that helps us gain a deeper understanding of the reality we exist in. This idea is not only remarkable, but also impacts various scientific fields. A black hole is a region in space from which nothing, not even light, can escape. In the 1970s, Stephen Hawking calculated that black holes emit radiation and gradually lose energy and mass over extremely long periods of time. This finding was crucial in understanding what happens to matter that falls into black holes. Previously, it was believed that black holes would exist forever, trapping everything inside with no consequences. However, Hawking's calculations show that black holes could actually evaporate and eventually disappear completely. This phenomenon, known as Hawking radiation, suggests that black holes are not entirely black and can emit particles and energy. The concept of Hawking radiation challenged the traditional view of black holes as eternal prisons from which nothing can escape. It introduced the idea that black holes can interact with their surroundings and gradually lose mass and energy. This discovery had profound implications for our understanding of the universe and the nature of black holes. To grasp the significance of Hawking's findings, let's take a step back and understand how black holes form. Black holes are formed from the remnants of massive stars that have undergone a catastrophic collapse. When such a star exhausts its nuclear fuel, it can no longer counterbalance its own gravitational pull. The star collapses under its own weight, compressing its matter into an incredibly dense object. This collapse results in the formation of a black hole, where the gravitational pull is so strong that nothing, not even light, can escape its grasp. The region from which nothing can escape is called the event horizon. Beyond the event horizon, the laws of physics as we know them cease to apply. Hawking's breakthrough came when he realized that black holes were not entirely devoid of activity. According to quantum mechanics, the branch of physics that describes the behavior of particles at the smallest scale, there is a constant quantum fluctuation of particles and antiparticles in the vacuum of space. These particles spontaneously appear and annihilate each other, usually too quickly to be detected. In the vicinity of a black hole's event horizon, this quantum fluctuation can result in a particle-antiparticle pair being created, with one particle falling into the black hole and the other escaping into space. The particle that escapes carries away energy from the black hole, causing it to lose mass over time. This process is known as Hawking radiation. Hawking radiation has several profound consequences. Firstly, it suggests that black holes have a finite lifespan and can eventually evaporate completely. The smaller the black hole, the faster it evaporates. This implies that black holes have a limited duration in the cosmic timescale. Secondly, the emission of particles and energy by black holes contradicts the classical notion that nothing can escape their grasp. While most of the particles created near the event horizon fall into the black hole, a fraction manage to escape, carrying away information about the black hole's properties. This challenges the idea that black holes erase all information about the matter they consume, which was a long-standing puzzle in physics. Now the realization that black holes evaporate over time raises a profound question. What happens to everything that falls into a black hole? So, when an object falls into a black hole, its fate depends on its distance from the black hole and the size of the black hole itself. As the object approaches the event horizon, the gravitational pull becomes increasingly stronger. If the object falls directly into the black hole, it will reach a point called the singularity, a region of infinite density and space-time curvature at the center of the black hole. At this point, our understanding of physics breaks down, and we cannot predict what happens with certainty. As we have discussed, some theories suggest that the object's mass and energy contribute to the growth of the black hole, while others propose that the object's information is preserved but inaccessible to observers outside of the black hole. However, before reaching the singularity, the object experiences a process known as spaghettification. The extreme tidal forces near the black hole cause a different gravitational pull on different parts of the object. The side closer to the black hole experiences a stronger pull than the side farther away. As a result, the object gets stretched and elongated, resembling long, thin strands of spaghetti. This phenomenon occurs because gravity's force decreases with distance, leading to a stretching effect called tidal stretching. The intensity of spaghettification depends on the size and mass of the black hole. Smaller black holes have more pronounced tidal forces, resulting in stronger spaghettification. Conversely, larger black holes generate milder tidal forces, leading to a less severe stretching effect. During spaghettification, the object is stretched into a long, thin shape, with the gravitational forces acting as powerful tugs in opposite directions. This process applies to any object falling into a black hole, including celestial bodies like stars or even humans. Now let's discuss another question. Is it possible to create a black hole by compressing the Earth? To create a black hole out of the Earth, we would need to compress its entire mass into a volume about the size of a blueberry. However, most black holes we know of are much larger, with masses billions or tens of billions of times that of the Sun, and volumes that would encompass our entire solar system. While it is theoretically possible to compress the mass of the Earth into a small enough volume to create a black hole, it would require an enormous amount of energy and a compression mechanism that is currently beyond our technological capabilities. Furthermore, getting a black hole out of the Earth would be catastrophic for our planet and everything on it. As for the observable universe, we are aware of its expansion, but the question arises, what is it expanding into? The answer is that it's expanding because space itself is expanding due to the specific nature of the universe's birth. It is important to note that the expansion of the universe is not an expansion into a pre-existing space, but rather an expansion of space itself. The fabric of space-time is stretching, carrying galaxies and other cosmic structures along with it. This expansion can be thought of as the stretching of a rubber sheet, with galaxies acting as dots on the sheet that move apart as the sheet is stretched. The rate of expansion of the universe is influenced by various factors, such as the amount of matter and energy present. Dark energy is thought to be driving the accelerated expansion observed in recent years. Additionally, there are parts of the universe currently beyond our observation, existing outside the so-called observable universe. The observable universe can be defined by the sphere around us composed of all the entities that have emitted light signals that we could receive. Since the speed of light is finite, we can only observe objects that are within a certain distance from us, corresponding to the time it took for the light to reach us. Beyond that sphere, there could be regions of the universe that we are unaware of. These regions are too far away for us to see because the light from those regions hasn't had enough time to reach us since the beginning of the universe. Now, let's explore an intriguing possibility. Is it possible that our entire existence is confined within the immense expanse of a black hole? While this idea may initially seem far-fetched, there is a fascinating possibility that, under specific circumstances, we could indeed be safe within its gravitational embrace. However, once we pass the event horizon, there would be no turning back, a one-way journey into the depths of the black hole. Nevertheless, the concept of our observable universe residing within the interior of a colossal black hole is not entirely implausible and merits further exploration. Black holes transcend being mere peculiarities of astrophysics. They possess extraordinary properties that challenge our understanding of the universe. The event horizon, for instance, acts as an impenetrable barrier, forever beyond our reach, regardless of our velocity or technological advancements. These celestial entities have the ability to consume matter and grow in size, presenting us with a tantalizing prospect. When considering the notion of being inside a black hole, we encounter an intriguing phenomenon, a point in space that perpetually recedes from us, akin to a distant horizon. Contemplate our earthly perception as we gaze into the vast expanse of space. There exists a boundary, a horizon that lies unimaginably far away, forever beyond our visual grasp. We possess the knowledge that something lies beyond this point, yet no matter how fast we travel, we will never be able to observe it. Strikingly, this parallels the experience one would have within the interior of a black hole. The mathematical framework governing the interior exhibits astonishing similarities to that of the exterior, lending credence to the idea. From a mathematical perspective, it is a notion that not only holds logical coherence but also aligns with our intuitive understanding. While the idea of inhabiting the interior of a black hole captivates our imagination, scientists rely on empirical evidence to substantiate any hypothesis. Thus, the natural question arises, how can we test the intriguing notion that our universe exists within a black hole? Perhaps indirect observations and theoretical models can provide insights and predictions that can be verified through experimental exploration. However, to embark on such a quest, we must first comprehend the intricate processes that give rise to black holes, what mechanisms are at play during their formation. To unravel the mysteries of singularities, a point of infinite density within a black hole, we must merge the principles of general relativity and quantum mechanics. These two fundamental theories have long posed a conundrum in physics, as their reconciliation remains elusive. By studying black holes, we hope to shed light on this perplexing question and uncover potential connections between gravity and quantum mechanics. Scientists relentlessly pursue a more comprehensive theory that unifies those seemingly disparate realms. The pursuit of understanding the formation of singularities requires a deep exploration of both general relativity and quantum mechanics. Within the realm of singularity, the laws of physics break down, presenting a daunting challenge. However, black holes offer a unique opportunity to explore these extremes and probe the limits of our current knowledge. While experimental evidence is crucial to sustaining the universe inside a black hole hypothesis, it remains a challenging task. Scientists strive to find innovative ways to indirectly observe, test, and gather data that can support or refute this captivating concept. The quest for knowledge drives our curiosity and compels us to unravel the mysteries that lie both within and beyond the boundaries of our observable universe. Life inside a black hole, if such a scenario were even possible, would undoubtedly be an extraordinary and perplexing experience. The extreme gravitational forces within a black hole would warp space and time to such an extent that our conventional understanding of reality might cease to apply. Within the event horizon, where the gravitational pull becomes overwhelming, the fabric of space-time would be severely distorted. Time itself would appear to slow down or even come to a halt from an outside observer's perspective. As we venture deeper into the black hole, the tidal forces would grow exponentially, stretching and distorting our physical bodies and the very atoms that constitute us. The immense gravity would disrupt any semblance of stable structures, tearing apart matter at its most fundamental level. Now let us know your thoughts in the comments section. If you enjoyed watching it, give it a thumbs up and click the subscribe button. Thanks for watching.